I now want to look at the idea of exterior angles. Here I have a triangle and I've extended out one of the sides and labeled a few of the angles. In Euclidean geometry, one of the most basic theorems we have is the exterior angle theorem that says the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2. And we want to see if we can expand on this idea in general. Let's look at a very specific triangle on the sphere, the tri-rectangular, the one with 3 right angles. When I look at an exterior angle, I'm looking at an angle like this right here, and we can see that the exterior angle inequality doesn't hold here. In fact, this angle here is equal to angles 1 and angles 2. The exterior angle inequality said that angle 4 should be equal to angle 1 plus angle 2, which doesn't work here. Let's start by actually defining what an exterior angle is. The idea is we need to start with a triangle ABC, like this one here. We start by letting D be any point such that C is between B and D, so any point that's on this extended segment between B and C. Then we have this angle ACD right here is known as the exterior angle. On the other hand, angles A and angles B are known as opposite interior angles. So the idea being this can be expanded to any side, and we would be able to talk about both the opposite interior angles as well as the external angle. Now that we have the idea of exterior angles, we can define the exterior angle inequality. The exterior angle inequality states that in any triangle that has sides less than alpha over 2, so we're going to exclude any kind of triangle that has more than one right angle, the measure of an exterior angle is greater than that of either opposite interior angles. So if I go back to the picture I had before, essentially what this says is that the measure of angle 4 is going to be greater than the measure of angle 1, as well as the measure of angle 4 is greater than the measure of angle 2. And while I won't prove this because it is a long detailed proof, we do see the general idea, and this is going to hold in both spherical and Euclidean geometry, with the one exception of triangles with multiple right angles. And this is why we have this condition that the sides need to be less than alpha over 2. This exterior angle inequality has a lot of results. The first says if the sides of the triangle are of lengths less than alpha over 2, so we can't have more than one right angle, then the sum of the measures of any two of its angles is less than 180. If I go back to my picture, I know that if I add up measure of angle 3 plus measure of angle 4, that I get 180 degrees, since these angles are supplementary. I know that the measure of angle 4 is greater than the measure of angle 1 and the measure of angle 2. So now I have that 180 degrees is greater than the measure of angle 3 plus the measure of angle 2. So the sum of these two angles will be less than 180. And once again, the measure of angle 4 is also bigger than the measure of angle 1. So this also works for angles 1 and 3. To show it works for angles 1 and 2, we would just need to extend out a different side here and use this exterior angle inequality on that side as well. My next result, any triangle that has sides of length less than alpha over 2, so no more than one right angle, has at most one right or obtuse angle. And this comes from the idea of the last one. If I have two obtuse angles, then I have two angles that add up to be bigger than 180 degrees, which is impossible. The same thing for two right angles. two right angles would be exactly 180 degrees, and I said it had to be strictly less than 180. And if I have one right and one obtuse, once again, that would add to be something bigger than 180, which I just said was impossible. The next one, if I look at the base angles of an isosceles triangle, having sides of length less than alpha over 2, then those base angles are acute. So let's say this is an isosceles triangle and these two sides are equivalent. I've already shown that means these two angles are the same. They can't be right or obtuse since I just said you could have at most one of those. So that guarantees that these two angles must be acute. My next one, if I have a right triangle with sides of length less than alpha over 2, then there is only one right angle. The other two angles must be acute. And this goes back to that idea that I could have at most one right angle or an obtuse angle in a triangle. My next big result that I won't prove but I will discuss is, let's suppose we have an angle ABC that's acute. So here I have A is this point, here's B, here's C. And we're assuming that the length between A and B is less than alpha over 2. Then, if I draw the foot D of A, so if I draw the perpendicular from A down to this line BC, that will be the point D, it's going to fall on the ray B and C, which it absolutely does in this picture. The opposite of this would be if we start with an obtuse angle here. We'll have this be ABC. When I try to draw the foot, I can see it's actually on the opposite ray for B, BC prime. So it's essentially saying that acute angles look the way we expect them to, and obtuse angles look the way we expect them to. Finally, the result of this, if I have a triangle ABC, so now I'm moving it back to in terms of triangles, that all the side lengths are less than alpha over 2, and I know that B and C are acute angles, so these angles down here are acute. Then the foot of A on line BC falls on side BC, so essentially, if I draw the foot from A to line BC, it occurs between B and C on this actual segment rather than outside of the triangle.